Today, we'll be presenting our Planet Pool capstone project, which involves optimizing pool flow. The team consists of Arthur Conroy, Daniel DeVito, Megan Lacoste, Stephen Moe, and me, Elise Velez. So just an overview, the topics of discussion for today. First will be objectives and scopes, background information, project design, summary of results, and lastly, the conclusions and recommendations that we found. So first, for objectives and scopes, we designed the circulation systems for 4 pools to ensure optimal flow conditions by using computer simulations to test the performance of each design and improve those designs. So these 4 figures shown here were given to us by Planet Pools. These are the animation drawings of the 4 designs that were used in this project, which include the rectangular design, freeform design shown in the top left and top right of the screen, Lazy River design and custom design shown on the bottom left and bottom right of the screen. Next, in our objectives and scope, we have our parameters of study. Shown below here on the right are 6 different kinds of bottoms that can be designed in a pool. For this project, however, we focused on the left, top, and middle pools seen here called the standard hopper bottom and the wedge bottom design. These 2 pool bottoms are called slope 1 and slope 2 shown here on the matrix on the left. One slope with certain injection points make simulation 1. The second slope with the same injection points makes simulation 2. The first slope again, but with different injection points, makes simulation 3. And the second slope with the second injection point location makes simulation 4. This means there were 4 parameters for each pool design, resulting in 16 total parameters for this project. Next, Megan will tell us some background information.
So some background on the piping and pumps used. So piping is used to transport fluids, while pumps are used to mechanically move those fluids. So with the pump, the water is taken from the pool through the drains and returned by the injection ports back into the pool, creating a circular motion. And so that's why choosing a pump plays such a large role in conducting the pool flow. There's 2 different types of pumps, the single speed versus the variable speed. So why does one need optimal pool flow? Well, it maintains the overall function of the pool, and it removes the debris and impurities from the bottom, and it distributes the chemicals that keep it clean. So flow has some relevance in other applications, including aquariums, ponds, and wastewater treatment systems. So aquariums, it sustains the life of animals, it removes the waste from the water, it exchanges the carbon dioxide for oxygen, which keeps the physical health of the animals living within good. So ponds also sustain the life of plants and animals. It removes waste too, creating oxygen-rich water, and decreases the algae growth. In water systems, it's for public health, water quality, and the environment, and it removes debris through several stages, and it creates oxygen-rich water. So using computational fluid dynamics modeling, or CFD modeling, which is the mathematical modeling of fluid systems using physical laws and numerical method techniques to analyze fluid flow. So designing a mesh for any physical model is an important role in determining the accuracy of a simulation. It involves the process of creating small cells, which produce a specific solution to that area. A solution is generated for each cell in the mesh. Therefore, the more cells there are, the more accurate the simulation will be. So the goal of CFD simulations are to achieve converged solution. This involves the use of numerical solutions going through an iterative process, which eliminates the errors from previous results. When the errors begin to decrease, the result resulting in a system converging towards a stable solution. So Daniel will give us more about the project design.
Okay, continue.
So next we're going to be talking about the pool dimensions of all the different style pools that were given to us. So the design team was given 4 separate pool top view dimensions that was supplied by Planet Pools to simulate flow in ANSYS Fluent software. So these 4 design dimensions were based off a traditional rectangular design, which is the top left pool, a freeform design, which is the top right, a lazy river, which is the bottom left, and a custom design, which is the bottom right picture. These are the geometric shape of the pools and served as the boundaries in the design system software. So next, the geometries that were made in SpaceClaim. Each dimension given was used to draw the pool geometries in SpaceClaim, along with each location of each injection point, skimmer, and outlet. The geometries for the first two parameter simulations were created in SpaceClaim. And after the first two simulations were ran, the data was analyzed and the injection points were edited and pretty much changed based on the specific locations that needed more circulation. This resulted in the last two parameter simulation geometries being created. So if you look at these pictures, you'll kind of get an idea for each style pool where the injection points, the skimmers, and the outflows were installed in the pools. And if you look at the pictures next to the pools, you'll see that these injection points and skimmers were all labeled to their respectful section in the name selection. Next, we're going to be talking about how the geometry was imported into the meshing phase from SpaceClaim. So the design team then created meshes using Fluent with the Fluent meshing for each of the geometries that were created in SpaceClaim. The meshes were created in order to capture relevant data in the solution mode. Also in the meshing phase, the boundary settings needed to be adjusted for each name selection that was created in SpaceClaim. So this allowed for the future boundary conditions to be set in the solution phase. So if you look in the bottom right-hand corner, you'll see the updated boundaries. You'll look at the boundary names, and each one of these names, like the bubbler injections, deep injections, main drain, these were set to their respectful function that was going to be done in the simulation for the pools. Next will be Stephen that will be talking about the simulations part.
So for the actual simulations, each member ran a total of 4 simulations on each pool design. The simulations were set up using the same settings, but each design only changed based on the boundary conditions that were specific to the uniqueness of each design. Simulations were ran in order to capture data and create visual results that would be used first attempt to improve the design and then decide if new designs were improved. The general settings that were used were multi-phase model, volume of fluid because the project involves 2 phases, both air and liquid water, and the viscous model was used with K-epsilon and standard wall fin settings. The specific settings for VOF models were open channel flow and open channel wave DC, then implicit formulation and implicit body force as well. The boundary conditions were set next in the solution phase. The boundaries that were created in the mesh portion that were the same name selections that were created in SpaceClaim now are finally going to be set in the solution mode to perform their individual activities. The conditions that were set to velocity inlets had to have their velocity magnitudes entered. If you look at the bottom left corner at an example here, these were bubblers, so the velocity magnitude was set at 1 meters per second for this particular example, because bubblers don't produce a very high velocity. Next, the conditions that were set for wall and outflow were left to default values. The top surface condition is set to a pressure outlet, and it needs very careful attention. That was first had to be set normal to the boundary, and then most importantly, under the multi-phase, open channel had to be checked, and then very importantly, looking at free surface level and bottom level. Very specific to the pool, the free surface level and the bottom level needed to be adjusted depending on how the pool was designed in SpaceClaim. This was to set the boundary of where the water was in the pool to give the top surface level and the bottom level. So this was going to create the boundary of what was in the pool. So for this particular example, the free surface was at negative 0.076 meters and the bottom of the pool was at negative 2.438 meters. This created the water boundary inside of the pool. The other part of the project design was to create the visual representations and the velocity measurement in the solution phase. So for the visual representations, each member had to create different velocity contours of planes and surfaces with the intent of showing dead areas of flow in order to aid in creating a design that was more uniform flow. These contours were used to aid in creating first a better design and then also to show if the design was actually better. The numerical data was captured as velocity averages to see first if the new design was achieved a higher velocity average. And then the second thing that was done was standard deviation. These were based on the planes that were created, and this was done to tell if the actual standard deviation got smaller, then we could tell if there was an actual more uniform flow by the standard deviation being smaller and the flow being less spread out. And next, we're going to have Arthur talking about the piping.
Another goal for this project is to design the piping system to find the flow rates and using the flow rates to be able to calculate the velocities through the pipes. In order to find the flow rates, a software Aspen was used to simulate this process. As you can see here, there are 4 designs for each individual pool. On the top left, there is the rectangular pool. Top right is the design for the freeform pool. The bottom left is the lazy river pool, and the bottom right is the custom pool. And we're going to use these to move on into summarizing the results of the piping system. In order to find the overall flow rates in the piping system, the flow rates for these pools branch off and they form a parallel piping system. And these individual injection points into the pools have to be added together to determine the overall flow rate throughout. After running the simulations, it was determined that for the rectangular pool, there was an overall flow rate of 54.99 gallons per minute. And after calculation, the velocity was 1.71 meters per second. And for the freeform pool, the overall flow rate was 49.71 gallons per minute and the velocity of 1.55 meters per second. Moving on to the lazy river pool, the calculations for the overall flow rate turned out to be 41.71 gallons per minute with the velocity of 1.7, with the velocity, with the flow rate of 41.71 gallons per minute and a velocity of 1.29 meters per second. And the custom pool had a overall flow rate of 59.06 gallons per minute and a velocity of 1.84 meters per second. Another process was to do a cost analysis in order to determine the cost of the materials for building the piping system. This includes the price for the pipe, also includes the cost for the fittings to assemble the pipe and a pump, depending on the size. And in the rectangular pool, it is determined that the cost for the piping system using a 1.85 horsepower pump was right around $1,731. And if you were to use a bigger pump at 2.7 horsepower, it would be roughly $1,981. And that is shown on the left. And on the right is the free-form pool, where using a 1.85 horsepower pump would roughly cost $1,760. And using the larger pump of 2.7 horsepower would be roughly $2,010. And in this slide, it shows for the custom pool, which is using only one pump in determination because when they redesigned the meshes to improve their flow, improve their circulation throughout their pools, they did not need to add any injection points. So for the custom pool on the left, it was determined that the cost for the piping system would be $1,777. And for the lazy river, which is shown on the right, would be roughly $1,642. Then we performed a cost analysis on what it would cost to power these pumps. And the costs were based off the average cost in Lake Charles, Louisiana of 7 cents per kilowatt hour. The cost to run the smaller pump of 1.85 horsepower at a total of 12 hours for a single day would be roughly $1.16 for the day. And based off of 12 hours a day for up to 5 years, it would cost roughly $2,085. For the larger pump, based off the same average cost per kilowatt hour, it would cost right around $1.69 per day for 12 hours in the day. And for 12 hours a day for 5 years, it would cost $3,044. Now we have Stephen to summarize the results of the rectangular pool.
So I'll start with the visual results of the rectangular design. Looking at the top left corner, we have the wedge 1 design and the wedge 2 design. And in the bottom right corner, we have the standard 1 design and the standard 2 design. These are the two different slope cases, wedge 1, wedge, and standard. So starting at the top, wedge 1 versus wedge 2. The shallow end, you can note that there are blue areas, and also on the surface, there's a lot of blue areas, which show that the blue means that zero, very low velocity. So in order to fix that, and same thing with standard 1, the shallow end and the surface did not have dead areas. So in order to fix that, added an injection point in the shallow end and at the deep end. And if you look at wedge 2 and shallow 2, and standard 2, you can see that the shallow end and the surface both have more green, red, and yellow areas, which means that there was more flow added to those areas. Now, just looking at one set of visual results doesn't allow us to draw any conclusions. So we'll go ahead and look at some other thing, another set of results, and then we'll look at the numerical data to make a better decision. Again, we'll look at wedge 1 versus wedge 2 and standard 1 versus standard 2. This is a view from the bottom of the different layers. This gives a picture of what was actually going on throughout different depths of the pool. It also shows the same, confirms the same picture, the same of what the other one did as far as the shallow end was concerned, that there's a lot of dead area in the shallow end. But it also shows that half of the pool on the wedge 1 and the standard 1 appears to have very low circulation. So the same change was made, adding another injection point to the shallow end and the deep end. And as you can see, the wedge 2 design and the standard 2 design, the shallow end picked up some velocity, and the entire pool seems to have more green in it as it picked up more velocity. So now we're going to look at some numerical data. This is the summary of the numerical data. So as can be expected, the velocity, the green shows the second run, the wedge 2, and the blue shows the original wedge 1. So the top is wedge 1 versus wedge 2, and the bottom is standard 1 versus standard 2. So at the top, we're looking at first average velocity versus time, then we're looking at standard deviation versus time. So for the velocity versus time, we put more flow, I put more flow into the pool, so it was expected that the average velocity was going to increase. But what also happened was the standard deviation increased. Well, that means that the flow became less uniform. The same thing happened in standard 1 versus standard 2, is that, yeah, I put more flow in the pool, so the average velocity increased, but I can't really say that the flow got any better because the standard deviation become more spread out, so the flow got less uniform. My recommendation here, oh, and another note, a larger pump was required, so more money, $250 initial cost for a larger pump, and about $149 a year at a cost to run this pump. So my recommendation to myself, if I could do this project over again, or if I could run more simulations, or a recommendation to whoever would continue with this project would be not to put more flow into the pool. The recommendation would be to manipulate the flow that was currently in going into wedge 1 and standard 1, keep the same amount of flow going in, just manipulate where it was going. Then if the average velocity was increased with the same amount of flow going in, then I would say with certainty that flow did get better. Plus, at the same time, if one was able to decrease the standard deviation while doing that, definitely one could say that they created a more uniform flow at the same time. So that would be the recommendation to myself or to another group if they wanted to pick up the project and take it from here. And that's the end of the presentation of my results. And I do believe Elise is next with the freeform results.
So to begin the summary of results with the freeform design, the first visual representations that I gathered were the velocity path lines. Path lines are very useful in complex three-dimensional flows because they show the path the injection points make throughout the domain of the pool. Here you can see the velocity range was set between 0 and 0.5 meters per second for all of the pictures shown. And the areas with no color that are kind of see-through show less circulation. So if you look at wedge 1 and hopper 1 designs, and you look towards the shallow ends of the pool, you can really see that there wasn't a lot of circulation happening. And even in the wedge 1 path line in the middle of the deep end, you can see here that there was missing some circulation. So for those reasons, 2 injection points were added, one to the shallow end and one to the deep end of both designs. So if you look over onto wedge 2 and hopper 2, you can see that the circulation definitely got better. There's still some spots that didn't get a lot of circulation in the steps for the hopper 2, but if you look at the wedge 2 design, you can see that the circulation is a lot better, especially throughout the steps, which is, the whole reason why we put those injection points. So between all the velocity path lines for each designs here, I would say that the wedge 2 is the best, but as Steven said, you can't make that conclusion just based on one visual representation, which is why I also gathered the visual representations for the velocity contour planes to get a better view inside of the pool. And the velocity range was also set between 0 and 0.5 meters per second for these contour planes. And they also show less velocity around the shallow ends here and the deep ends here in these planes with the wedge 1 and hopper 1 designs. And so again, if you go to the second designs here in hopper 2, you can see this plane where the injection ports came in. There's more flow here, it has more color, and that means that there's more velocity, more green. And especially if you look at wedge 2 here and all of these planes, you can definitely see the difference between wedge 1 and wedge 2 velocity difference and see that there's a lot more here. But that was expected because 2 injection points were added here. And so even though wedge 2 also seems to be the best visual representation for the velocity contour planes of all the designs, you can't really conclude that based on these, which is why numerical data was also gathered. So looking at the average velocity for each design, the graphs at the top show that wedge 2 and hopper 2, the yellow lines, have a higher average velocity than the wedge 1 and hopper 1 lines. As mentioned multiple times, because there were 2 added injection points, this was to be expected and doesn't really tell us which design has a better circulation. So to tell us which has a better circulation, the standard deviation throughout the pool was found. And it looks like the standard deviation here for the 2 new pool designs is lower than the original designs, which means that the data is more uniform and contains a better circulation, along with the higher average velocities found. Now, between the wedge and hopper designs, both of the wedge designs have a better standard deviation data than the hopper designs because the standard deviation is lower than the hopper designs. So based on the visual aids and this data, especially the standard deviation data, the wedge 2 design is the best design of the 4. But because of the added injection points, like Steven said, and Arthur mentioned, a bigger pump has to be used, which means a higher cost of $250 is needed to buy the pump and the pipe, and a yearly added cost of around $190 is needed to run the pool yearly. Now, looking closer at the standard deviation between wedge 1 and wedge 2 designs, there's only a difference of about 0.01 meters per second. And because of that, I would say it's not cost effective to pay more for this amount of circulation difference in the pool. So because wedge 1 has the next best standard deviation, wedge 1 would be my recommended design for the freeform pool out of all of the designs. And if this part of the project were to be run again, I would not add injection points, but just move the existing ones, whether it be to completely different locations or even just angling them in a different direction would be fine, just as Steven said. So this concludes my results for the freeform pool, and now Daniel will summarize his results for the lazy river design.
Okay, so next we're going to be talking about the data and results for the lazy river design. That was mine. So the pictures I have shown here are the velocity path lines that was also shown in Elisa's design. So for accurate comparison of all 4 of these pictures, the velocity range was set between 0 and 0.1 meters per second, so we can get an accurate comparison. And we'll go ahead and start off with the wedge 1 design. So if you look in the top left picture, you'll see that the flow in the pool was pretty uniform, distributed throughout the entire volume of the pool. There was one dead spot that was located at the steps, the shallow step section of the pool. So in order to compensate for that, if you look over at wedge 2 on the right side, you will see that an injection port was added to help eliminate the dead spot there and to help increase the flow. Next, going down to hopper 1, which is the bottom left picture, the overall circulation of the pool was also pretty good, just like in the wedge 1 design, but similarly to wedge 1, there were still some dead spots over there in the shallow end of the pool where the steps were. So going to the new hopper design in the right side, an injection port was also added there to help eliminate the dead spots. Overall, looking at that picture for the wedge 2 and the hopper 2, you can see that the circulation was greatly increased from those over there in the wedge and hopper 1. But just like that they were talking about earlier from the assumptions of these pictures shown for the velocity path lines, it was assumed that wedge 2 is the best design, showing the best circulation, and that hopper 2 would be a good alternative design. However, like they were saying, you can't make those decisions off these results, and you'll see later why we chose those 2 as our best designs. So next we have some velocity contour planes shown. And for accurate comparison between these designs, we had the velocity set between 0 and 0.5 meters per second. So again, looking at wedge 1, you'll see in the steps area of the pool, you can see it was dead. And just like in the pictures shown in the last slide, going to wedge 2, you'll see that the velocity in the steps area of the pool was also increased by adding that injection point. Going down to hopper 1, you'll see the similarly to wedge 1 that it was also a dead spot in the shallow end of the pool. Therefore, going to hopper 2, it increased the dead area of the pool with the injection port. So the purpose of showing these planes right here for the velocity contours, so they kind of give us an idea of the how the circulation was on the inside of the pool. Because the velocity path lines, it was kind of hard to see what was going on the inside, and that is why these velocity planes were shown. So lastly, we're going to talk about the numerical data for the average velocity and the standard deviation of the lazy river design. So if you look at the first chart in the top left corner, you'll see that the velocity average between the original wedge and the new wedge were not that different. So that is okay because the whole purpose of adding the new injection port wasn't necessarily to increase the average velocity, but it was pretty much added to just eliminate the dead spots in that shallow end of the pool. So by looking at the graphs and seeing that the average velocity didn't change, that was completely okay. Next, if you go over and you look at the top right picture with the hopper design, you'll see the comparison between the original hopper and the new hopper design. You'll see that initially they kind of start off at a large difference between the average velocities, but you'll see as the pool begins to stabilize, you'll see that the pool velocity starts to get very close again, similar to the original and new wedge. Next, we're going to look at the velocity standard deviation versus time for the original wedge and the new wedge. So by looking at the bottom left picture, one thing that you're probably noticing is you'll notice that the velocity standard deviation in the new wedge was a lot higher than the original wedge. So obviously this data right here is wrong, and a recommendation for future projects to look into this would be maybe there was something created wrong in the geometry, or there was something in the boundary conditions that wasn't set up right. But time permitting, there just wasn't enough time to go back and rerun the simulations to try to get better results. So next, if we go over to the right picture, you'll see the original hopper versus the new hopper design. So according to the data, we made the assumption earlier in our contours that the wedge 2 design was a good alternative, or the hopper 2 design was a good alternative to the wedge 2 design. So when you look at this data, you'll see that the new velocity standard deviation for the new hopper was actually lower than the original hopper, pretty much backing up the data that it would be a great alternative to the wedge 2 design. One last thing to kind of say about these designs is that to add the injection point, it actually, a new pump or a bigger pump was not actually needed to add an injection point. So the annual operating cost would not have been increased. The only increase in price for adding an injection point would just be for the piping. So that was a big plus in adding the injection point as to where it wouldn't be charging as much money. So the last in conclusion to pretty much say about this part of the project was that the wedge 2 design was the best design visually. However, numerically, it could not be backed up. Now, if you go to look at the wedge 2 design, you do have that numerical data to back up the claim that it had the best overall circulation of the pool shown visually. And this concludes my part of the design. So next, Megan's going to be talking about her custom design.
So we'll start off with the path line plots of the pools. The top two will show the hopper design 1 and 2 respectively, and the bottom two will show the wedge design 1 and 2 respectively. And so the range for these plots per second to 1.2 meters per second. So looking at hopper number 1 with the original injection points, you can see that there is some flow in the left of the pool and that there's good circulation there, but on the right, there's kind of a stagnant area in the middle. And so moving on to the second hopper design, no injection points were added. They were just moved around. And so you can see that there that we lost the circulation a little bit on the left, but the circulation or the stagnant area in the middle was improved. And so moving on to the wedge 1 design, which uses the same injection points from the first hopper, you can see that there is definitely an improvement in the circulation from the first hopper. And so going into the second wedge design, the assumption was that because there was a slight improvement from the first hopper design to the second, an improvement from the first wedge to the second. You can see that there is some improvement on the right of the pool in circulation, but there's a large stagnant area in the middle of it, which was not good. So overall, if I had to make comparisons, hopper 2 shows better circulation than hopper 1, and wedge 1 shows better circulation than wedge 2. But again, you can't get results based off of one visual representation. So the next slide shows the contour planes. So again, the hopper designs are on the top and the wedge designs are on the bottom, and these have a range of 0 meters per second to 1.23 meters per second. So again, looking at hopper 1, you can see that there's the large stagnant area in the middle, but overall, there's a good circulation throughout the pool on the bottom a little bit. So moving on to hopper 2, you can see that some of it was fixed. There's still a little bit, and the overall circulation on the left decreased a little bit. But overall, the circulation in the right improved. So moving on to wedge 1, you can see that there's quite a bit of good circulation throughout the pool, except for the stagnant area on the right a little bit. And so moving on to wedge 2, the circulation isn't quite as good. It fixes the stagnant area on the right, but the overall circulation comparing the two just isn't as good as the first one. So again, if I had to compare them, the wedge one would be the best pool overall, while the second hopper would be a close alternative. So moving on to the data analysis, the numerical analysis. Graph 3, we'll look at that one first, shows the average velocity. Because no injection points were added for any of them, all of them had the same line going up, except towards the end, where you can see that wedge 1 maxes out a little bit more than the others, which makes sense going back to the pathline plots where the circulation was better overall. And so now we look at the standard deviation of the hopper design, which is the first graph, and you can see that backing up our visual aids, the standard deviation of the hopper 2 design is lower than that of the hopper 1 design. And then looking at the wedge design, it kind of contradicts what we saw in that the wedge 2 design has a lower standard deviation than the first one, where the wedge 1 from the visual representations had better circulation. But the hopper designs had a lower overall. But so in conclusion, I'd say that wedge 1 overall had the best for the custom design, and the hopper 2 would be a very close alternative. There was no cost benefit because no injection points were added, so a bigger pump was not needed. And so my recommendation for if anyone else was to use this project was to be add injection points, 1 or 2, to see if a bigger pump needed to be used, and if so, the cost of that over 5 years, and then to maybe change the locations of them to fix that stagnant area that was still there a little bit. And so now we'll have Elise concluding our presentation.
So just to conclude the project summary for this presentation, we went over how we designed 4 different pool geometries and chose the best design based on the visual representation and the numerical data for each of the 4 pool designs. How we calculated flow rates based on each pool design to include piping and pumps, and covered those cost analysis for each of the piping designs and annual operating costs of up to 5 years. Thank you for your time, and thank you to Paul Glasgow from Planet Pools. Are there any questions?